In this video we're going to be looking at an example of some of these vector products worked out for a couple of 3D vectors. So here we have vectors. They're given by these boxes here in green and blue. So these are the components of U, the X, Y, and Z components, or first, second, and third components, or I, J, and K components you might say. And similarly these are the three components of V. So right at the moment we see that U is the vector 1, 3, negative 2, and V is the vector 2, negative 1, 4. So the first thing I'm going to do here is compute the norm of each vector, or the length. And so we just square each component and add them up. 1 squared plus 3 squared plus negative 2 squared. Let's see, that's 1 plus 9, that's 10, plus another 4 is 14. So this is the square root of 14, or about 3.74166. Then we can do the same way for V. 2 squared plus negative 1 squared plus 4 squared. So that's 4 plus 1 is 5 plus 16 more is 21. So it's the square root of 21, or about 4.58258. Now, if we multiply a scalar times a vector here, so if we multiply vector U by 2, we're multiplying each component by 2. So 2 times 1, 3, negative 2 is 2, 6, negative 4. And what that's going to do, it's going to leave the direction the same, but it's going to be, well, twice as long. So the norm of 2 times U is 2 times the norm of U. So the norm of U here was about 3.7. You say 3.74, double that, that's 7.48, which you can see is what it is here. Now let's compute the dot product. To do the dot product, you just multiply corresponding components and add them up. So we do 1 times the 2, 3 times the negative 1, plus negative 2 times the 4, which is what I have here. So that's 2 minus 3 minus 8, that's negative 9 for the dot product. Now one way we can compute the angle between them is by finding the arc cosine of the U dot V over the two norms. So another way to get the dot product, U dot V, is to take norm of U times norm of V times the cosine of the angle between them. Or, solving for theta, this is how we can get the angle. So the dot product we computed is negative 9, the two norms are square root of 14 and square root of 21, and so the inverse cosine of that is the angle. That works out to be about 2.12338 radians, or about 121.66 degrees. Now, illustrated over here to the left, you will find the vectors. So the green vector is vector U, the blue vector is vector V. No matter where these are, we can move them around so that they start tail to tail at this point right here. Okay, and we, regardless of where we begin, we can put them that way. And there is some plane that you can turn to and see both of these vectors in the same plane, and that's the plane that we're looking at here. And so this angle between them is this 121.66 degrees, or about 2.12 radians. So that's the angle right there between the two. Now, the dot product is negative 9. We'll come back to that in a minute. Let's talk about the cross product. The cross product is a vector, and if you use the right-hand rule going from U to V, you'll see that the vector, we could place it right here at the vertex here, but it's pointing straight out of the screen towards you, the viewer here. So it's coming straight up out of the plane, perpendicular to the plane, toward the viewer. Now, how big is that? Or let's actually compute that vector. Well, the way we do is we write ijk, ij. We write our vector 1, 3, negative 2, and then our second vector 2, negative 1, 4, and then recopy the first two columns here. Then we go upward, downward diagonals will be pluses, upward diagonals will be minuses. So to get the I component, our first component, we're doing this diagonal, which is 3 times 4, and minus this diagonal here, negative 2 times negative 1. So let's see, that's 12. 3 minuses make a minus, so 12 minus 2 is 10. Okay, similarly to find J, we go down the blue, down this diagonal for positive, negative 2 times 2, and then we subtract, going up this way, negative 2 times negative, let's see, over here, 1 times 4. There's the J diagonal. Okay, and I believe that's what I have here. Okay, so that's negative 2 minus 4, negative 4, 2 times 2 is 4. Negative 4 minus 4 is negative 8. Okay, to get the k component, here it is right here, go down the diagonal, 1 times negative 1, minus, come up the diagonal, 3 times 2, or 2 times 3. And so this is negative 1 minus 6, that's negative 7. So the vector that's pointing straight up out of the screen is the vector 10, negative 8, negative 7. The norm of that vector, well, of course, is the square root of 10 squared plus negative 8 squared plus negative 7 is approximately 14.59456. Okay? Or I guess, let's say it'd be 100 plus 64 plus 49, whatever that is, square root of that would be the exact value, but it turns out to be approximately this. Now that number right there, that 14.5 whatever, is the area of that parallelogram right there. So that the size of this parallelogram, the number that you get for the size, is the same as the length of the cross product vector. If we do a unit vector in the direction of v, it's found by taking v and divide by the norm of v. So we just take each component, take 2 divided by, so it's 2 over square root of 21, negative 1 over square root of 21, 4 over square root of 21, or approximately here. Now, we can do a projection of u onto v. And so that's the projection of u in the direction of v is this orange vector, and then the horizontal or normal component of that is the pink one. So the orange one is the projection of u in the direction of v, and the pink one is the projection of u parallel to v. So you have these two components. How big are they? They have something to do with the dot product and the cross product. So the orange one is, well, the size of it is the size of the dot product divided by the norm of v. So it's negative 9 over square root of 21, or an absolute value of that. So it's approximately 1.96396. Notice it's actually negative before we take the absolute value, and that says it's going to be pointing in the opposite direction of v. When the cross product is negative, then your projection is going to point of u onto v is going to point in the opposite direction of v, and similarly the projection of v onto u will point in the opposite direction of u. But if the cross product is positive, they'll point in the same direction. Okay? Now the actual vector then we can get by taking a unit vector in the direction of v, which was this one right up here, this unit vector here, and multiplying each component by this size here. Well, not by this size, but by this number here without the absolute value. So the signs are going to change. It'll be negative, positive, negative. So it'll end up being the opposite direction. And this is what those numbers turn out to be approximately. You can check those out with your calculator. So that's the size of that, or well, that's the size of it is about 1.96. So let's kind of look at the sizes of these things. The green one is about 3.7. The blue one's a little longer, about 4.9. And the orange one is about 2. And so to find the pink vector, to find its size, it's the norm of u times the sine of theta, which is the size of the cross product divided by the norm of v, which turns out to be 3.18479. So this is about 2 for the orange one, about 3.2 for the pink one. So the cross product and the dot product have something to do with these orange and pink vectors. Basically, the size of the orange one, the one that's in the same direction as v, or same or opposite direction as v, parallel to it, that one is the size of the dot product divided by the size of vector v. And the one that's perpendicular to that is the size of the cross product divided by the size of vector v. Of course, the longer you make v, the bigger you make both the cross product and the dot product. So, of course, if v is just a unit vector, that basically just gives you a direction here without really contributing to the length. Then the orange, if v was a unit vector and we did the cross product of these two, we would get the length of the pink vector, and the unit vector in the direction of v. Dot product with u would give you the length of the orange vector. Changing the length of vector v doesn't change the pink and the orange vectors, but it does change the cross product and dot product. Okay, so another way to think of this is dot product and cross product is this. The dot product is sort of a measure of how much of this vector is parallel to v. First of all, if the dot product is negative, the u and v, the component of u in the direction of v is actually in the opposite direction of v. And if the dot product is positive, they're kind of going in the same direction. If the dot product is 0, they're actually perpendicular. So if u is sort of pushing with v, then you've got a positive dot product. If the u is pointing in the opposite, away from v, you get a negative dot product. If they're pointing perpendicular, you get a 0 dot product. If u and v are actually parallel and they're actually going in the same direction, the dot product turns out to be just the product of the two norms. Okay? And if they're opposite, then we get the opposite of that. Okay? So the dot product is sort of measuring how much of this is pointing with it. The cross product, in a way, in addition to measuring the size of this parallelogram, it's sort of measuring the size of this vector here, because the cross product can sort of be thought of as a measure of how much of this is perpendicular to v.